Okay, so here we're looking at a familiar looking system of differential equations if you've watched the previous videos in this section. Here, x is denoting like the rabbits and y is denoting the foxes. But I'm going to use x and y and just look at these dynamics in general. So in the previous vector field, we saw that at points where the derivative dx dt is equal to 0, these are going to be points in the phase plane where, since dx dt is 0, the vector is going to have no horizontal component, and they're going to point straight up or down. So these points we call x nullclines. And the way that we find these nullclines is we're going to set dx dt equal to 0 and then solve for x and y. So we're going to find points that are going to make dx dt equal to 0. And so if I have this differential equation, x prime, I can factor out an x and we see that we have two nullclines. So these nullclines are going to be curves of points, in this case lines, and so we see we have one nullcline on the line x equals 0, and if we were to solve that equation we would get a second nullcline when y is equal to 2.14. So I'm going to plot these lines in the phase plane. So x equals 0, that's the y-axis. So I'm just going to put a little dashed line over here. And then the other nullcline is through the horizontal line, y is equal to 2.14. So that would be approximately over here. And what we might want to know is, we know that these verticals point straight up or straight down, and whether they point up or down, that really depends on the y prime equation. So if I were to do some analysis with the sign of y prime, we could say, for example, if x is equal to 0, then this equation for y prime, that's what I'm interested in seeing, is what's the sign of y prime. Y prime is equal to minus y. And so what we can see is, if I'm on this line x equals 0, then what's happening is, if y is negative, then minus y would be positive, right? And that would tell me that y prime is positive. So when y is negative, these vectors are going to point up because dy dt is positive. And on the other hand, when y is positive, then y prime would be negative, and that's why these vectors are going to point down along this x nullcline when y is positive. Okay, and so we still have some work in terms of figuring out how the vectors are pointing up and down along this other x nullcline, but I'll come back to that in a sec. So we can look at a similar idea, we've seen this, that we get important behavior as well at any point in the phase plane when dy dt is equal to 0. We call these y nullclines, and all of the points along these curves are going to point directly to the left or to the right, because they're going to have no vertical component to those vectors. And so to figure out how to find the y nullclines, here it's a similar process, but now we set the equation for dy dt equal to 0. So here we would set y prime, which is, we could factor out a y from the equation, and we would get minus 1 plus 0.8x. And we can see that this is equal to 0 when y is equal to 0. So that means we have one y nullcline along the x-axis when y is equal to 0, and we have a second nullcline when that other factor is 0, and that's going to occur when x is 1.25. So we have a second nullcline, y nullcline over here. And then we want to figure out whether these vectors, we know they're pointing directly to the left or to the right, but is it to the left or is it to the right? And so here we can do a similar sort of analysis, and we can say, well, if y is equal to 0, so I'm going to consider the nullcline along the x-axis. Now we would want to look at what's the sign of x prime, because that's going to determine whether we go to the left or to the right. And so here we can see that x prime, if y is equal to 0, then this term goes away in the differential equation for x. And what's left is x prime is going to equal 3x. And so we see that if x is bigger than 0, then x prime is going to be bigger than 0. So for all of the points along this curve, which is a line, as long as x is positive, so when I'm over here, we see that the vectors are pointing to the right because x prime is positive. So I'm going to plot these vectors over here. They point to the right. And same idea, we could identify that these are pointing to the left. And I would encourage you guys to think about what to do with the other nullclines. The analysis is the same. Maybe the algebra is just slightly more difficult. But what you should be able to show is that along the nullcline for y is equal to 2.14, as long as x is bigger than 1.25, you'll see that in this case y prime is positive, and that's why these are pointing up. And when I flip and all of a sudden x is less than 1.25, then these vectors point down. And if we were to look finally at the nullcline when x is equal to 1.25 along this vertical line, what you could verify is that in this case, if we set x equals to 1.25, then what we can see is that when y is bigger than 2.14, you should see that x prime is going to be actually negative. So that means when y is bigger than 2.15, these vectors are actually pointing to the left. So that would mean we've got these vectors pointing to the left, and then when y becomes less than 2.15, x prime becomes positive, and now our vectors point to the right. And in the middle of all of this, since this is the rabbit and fox problem that we've been following, it's worth pointing out that we can see, I won't draw it perfectly, but we can see this sort of pattern in the solution that we're getting this cyclic behavior, which is moving counterclockwise around that equilibrium, which was right in the middle. That equilibrium was located right there when x was 1.25 and y was 2.14.